In SOAR, our mission is not only to build underwater remotely operated vehicles, but is to find innovative and inexpensive solutions to solve problems. SOAR consists of 9 students, from freshman rookies with no experience to 4-year senior veterans who are acclimated to the engineering process. Our main ROVs are our Isle Royale, Rookie, Demo, and Compact ROVs. We'll also show you some of the ways we innovatively solve problems.
What is SOAR? Founded in 2010, SOAR is a student-led organization based in Delaware Bay High School. Specializing in building ROVs, SOAR allows students to gain experiences in areas such as coding, design, electricity, manufacturing, and troubleshooting. Each day, challenges are taken on where failures often happen. We embrace our failures and learn how to move forward. Our main focus is providing technical solutions to issues within our community.
So when you first joined SOAR, you were considered a rookie, and your goal is to retrieve an underwater T, and you make ROVs in class, and you trial and error, and you can use models from different people who have graduated from Delaware Bay and people who are in the class right now. So you have a budget of $400 to make parts and 3D print and trial and error and test your ROV out in the lake, and yeah.
The biggest challenges we would face is when something would break on one of our ROVs. It was really difficult to replace because of the connectors we were using, and we would even sometimes have to take apart the entire ROV to get to the broken piece. Another problem with the system we were using is we had to use screwdrivers or hex keys to get out the pieces, which we could drop in the water and easily lose. But with the new dovetail connectors, we can easily replace and fix broken parts to any of our robots without any tools.
Our goal for the Isle Royale ROV is to make it durable and easily repairable. All the structural parts are 3D printed, so they're easy to produce, especially because up here in the UP, you have to wait for long shipping times on anything complicated or injection molded. The pins are small and light, so if one breaks, you can have a replacement in the field. And we use the dovetail system to allow you to easily disconnect batteries, allowing for much longer mission times because you don't have to recharge them after each trip. We also have a very forward camera, letting you have a very wide field of view, perfect for inspecting things.
One of the latest improvements we've made on our ROV is refining the backplates. Our old backplates were made with epoxying wires in between 2 acrylic plates. These are bad in many different ways. One is that they are really hard to troubleshoot. The wires are locked into place, so you cannot move them or look at where they are inside the backplate or to find out where the problem is. Another thing is that when you find the issue, you can't independently change or adjust the wires inside the backplate, so you have to replace the whole backplate. And the last problem is it doesn't look good. It looks unorganized and unprofessional. Our new design uses Deutsch connectors epoxied into place. This is better for many reasons. You can independently unplug each wire to troubleshoot and easily replace the bad wires because they are not locked into place. It looks significantly better and more organized and professional.
So in class for the ROVs, we use and make cameras in class instead of buying a whole camera online. So one of the reasons why we make cameras in class instead of buy online is because when you buy, it's more expensive and they're more easily breakable and we're not exactly used to them. So when we were first making these, we have 2 pieces of acrylic and then we mill them out to the shape we want. And then we have a PVC to actually hold the camera in. And then we have bolt holes to hold it all together. And then we use 3D printed parts to mount the camera to the position we want. And then we pressure test it in school. And to make the camera actually work, we use Deutsch connectors and BNC connectors. And then we have a tether on the back of the ROV, and we bring it all the way back to land to make it work.
Our demo ROVs are used to mainly introduce kids into robotics. They are similar to our rookie ROVs with their design, but instead of a bulky control box, they use an NES controller. We use an NES controller because it is more likely that kids would be more familiar with a Nintendo product than they are with a box with switches. It also shows them the cool things they could do as an engineer. Another improvement from the rookie ROVs to the demo ROV is instead of using pool noodles for our buoyancy control, we use buoyancy tubes, which are just sealed tubes with air trapped inside. This is a lot better because we can use math equations to figure out how much buoyancy tube we need rather than just guessing and revising with pool noodles.
The job of the compact RV is to be portable enough to be taken apart and carried in a backpack, but powerful enough to provide sufficient exploration of areas such as inland lakes or underwater caves that may require a hike to get to. One of the game changers for me was using the dovetail connectors that Avery talked about. These make the compact RV significantly more portable. The dovetails allow the RV to be taken apart in a short period of time, which also makes it small enough to fit inside a backpack and carried on a long hike. Proudly sponsored by Delaware High School, thank you for watching. Now it's time for us to get back to work.